All right, so here is our course content for NextGen Geospatial. This is our GitHub page where we just keep all of our content. I'll just scroll down here to our calendar, go by nice pictures of Carlos and I. Okay, and to our schedule. So today is February 6th, 2024. And today is going to be Intro to Cloud Native, and also we'll do an intro to Cyverse. And so this is kind of our introduction or beginning of talking about cloud computing. And so today's session is just going to be kind of conceptual. We're just going to talk about ideas and technologies. We're not going to be doing actually any live coding or Jupyter notebooks or anything like that. So just kind of sit back and take in some of the material. Please ask questions in the chat or just shout me down in the middle of what I'm talking about. So today is just going to be kind of a survey. We're going to go through several different, I'd say, components or aspects of cloud native, not going too deep into any one of them. We're just going to touch on kind of what I see are the elements of cloud native geospatial. And then in the subsequent sessions, let's say like February 13th, February 20th, 27th, and then after spring break, March 12th, we'll go into specific cloud native formats and get a little deeper into those formats. How do we use them? And then each of those sessions is probably going to have a little bit of a coding element to it. But today is just going to be conceptual. So let's go into my lecture material, Intro to Cloud Native. Okay, here's the material. Of course, I have to have my AI image on the front page. Not sure what my prompt was, computers in the cloud or something like that, but I always love the images I get back. Okay, so let's use the cloud. Don't worry about reading the text. The text is for people to access this stuff, by themselves online, but just listen to my voice and look at the graphics. So when I say let's use the cloud, I'm saying let's move away from kind of the typical model of GIS and geospatial, where we're using desktop computing and we are downloading data. I'm not saying that that model is broken or wrong. I'm just saying that there's a different way to do it. Instead, let's use the cloud. And when I say the cloud, I mean the internet. There are tons of cloud resources or internet resources that are out there that can be used for storing data, for computing, processing data, for sharing data. And we can almost do complete workflows all online, which can really help with several things, including increasing transparency of what we're doing. It can improve reproducibility, and it can just help us share a little bit better with our fellow researcher of what we're doing. So with cloud native geospatial, I'm trying to move from the conventional model of the download model of data and move it to cloud native model, which is we can stream data. And so we'll talk a little bit about what that means, but think of it in terms of like downloading a movie from the internet or streaming a movie over Netflix. It's the same idea. We can stream data directly from storage, cloud storage, to any application. So we can just kind of do an entire workflow all online. Yeah.
Like big pro to go from downloaded to cloud? Would it just be that you could move to different machines and keep working?
Yeah. So the question that a person in the room said is like, why cloud as opposed to download, the typical model? A lot of times that can be scalability. You can have access to much larger resources. I can have a laptop computer and then tap into all kinds of really large resources. I don't have to spend the money to have my own, expensive equipment. So that's one aspect. Another one is just shareability. I can just grab data from all kinds of sources instead of trying to have them, instead of trying to download them all to my machine, which you can do, but we're working a lot of times in gigabytes and really large file sizes. So I say that's a couple of reasons. And I'm not saying that the the conventional model is wrong or broken, or you should never do it. This is just a different way to do it. And yeah, working through your laptop and tapping into other computing resources and storage resources, to me, becomes easier to work. I can just take my laptop and go anywhere and not have to worry about, is my hard drive with me, or things like that. And so it frees you up, I believe, a little bit in terms of how you work and where you work.
I can tell you another experience. I have been doing hydrological modeling. So you go and look for the specific digital elevation map, and usually will be just a large space. But I just need the information from a specific watershed. So if I'm using cloud computing, I'm just go and get the specific information at the resolution I want, like Google Maps. You don't have to download the whole Earth. So as long as you start zooming, then the information will start arriving. But you don't download like 1 terabyte of data just to look for a specific size of map.
Okay. Well, yeah, that's what we're going to tackle today. Is basically kind of just some basic elements of cloud computing and why we're doing that for geospatial. So let's start with cloud storage. Data storage. Okay, so the typical model is we have a large hard drive on our local machine, or maybe we have a server, that our lab group or our organization taps into, and that's where we keep our data. There's nothing wrong with that. That works really great. But we are in the business of open science, which meaning like if you have data sets, chances are someone else might get some value out of them. And if we put them up in object cloud storage, then they are just hot and ready for anyone else to grab and use. But when I mean cloud storage, we have the typical, three-headed monster, Amazon S3, Google Cloud Storage, and Microsoft Azure Blob Storage. So those are all great options. With object cloud storage, everything you put in there has a unique URL. And so it makes it really great for input, output, sharing. But those commercial cloud providers are expensive. I'm in the business of drone imagery, and we reach terabytes really quickly. And so if I have terabytes of data in Amazon S3, I'm going to be paying a lot on my credit card. So we are in favor of more kind of like for the research and academic community, we have our in-house object cloud storage called the Cyverse Data Store. That's here on U of A's campus. And there's also something called the Open Storage Network. And if you click on that link, it'll show you other places across the country that have have data storage that's geared more towards the research and academic communities. So it's probably low cost or free. Yeah, so we'll talk a bit more about Cyverse Data Store a little later on the talk. So yeah, so in the cloud native model, data is up in cloud storage. You can just grab it through a URL. It makes it super easy to just grab data from anywhere or share data to anyone in the world. All right, so more about data sharing. So when it comes to sharing data, we talked about the download model versus the streaming model. And I had to put this analogy in. It's like going from the original Napster model of downloading music to the Spotify model of streaming music. How many people are downloading music anymore these days? I mean, maybe some people, but I don't anymore. I just stream it from YouTube or from Spotify or whatever. And we can do the same thing with geospatial data. What helps facilitate that is something called cloud native formats. And so these are geospatial data formats that you guys have probably heard of, but they've been tweaked just a little bit to make them specifically formatted for the internet, or HTTP, for the cloud. For instance, if you are working in vector land, you have a road network or a stream network or something. Instead of it being in a shape file, it could be in something called a flat GeoBuff. Similar. There's also something called the cloud optimized point cloud, which you see right here, or the COG, as its acronym is. So a cloud optimized point cloud is, it's a geotiff, or sorry, did I say point cloud? I'm getting confused. So this is cloud optimized geotiff, and then cloud optimized point cloud is COPC. But the idea is the same, is that there's formats that we are familiar with, and then we can tweak them just a little bit to make them more useful for streaming directly over the internet. If you are working with multi-dimensional arrays, there's something called ZAR, an X array that's built just for this purpose as well. And so with these cloud native formats, COGS, COPC, ZAR, flat GeoBuff, the idea is that they just sit in cloud storage, hot and ready for anyone to grab them. And then if someone's interested, they can just get the URL and stream that data directly into a client application. That could be into a Jupyter Notebook, that could be into ArcGIS, that could be into QGIS. And the idea is that you are not downloading the data, but you're just streaming like the parts of it that you want. Let's say you have a stream network and it's the entire United States. That's probably gonna be a lot of vector data. That could be gigabytes and gigabytes of information. With this streaming model, I could just request, in a way, just like the area of interest in my little study area, based on what the extent of my screen is, and I would get just that instead of downloading multi-gigabyte data file. I can just stream like what I want to see instead of bringing everything. And so the analogy is like a YouTube video. I'm not downloading the whole video. I'm just streaming little bits of it at a time, in the time, the area of the video that I actually want to watch. So how does this streaming thing work? I'll give you an example. So COGS, or Cloud Optimized GeoTIFF, it's just a GeoTIFF. So it's the GeoTIFF, the same GeoTIFF. It's a raster format. It's a very common format for imagery, satellite imagery, aerial photography imagery. And we can cloud optimize it, which means we bake directly into the file tiles and overviews. They get baked directly into the file. So when you're in a GIS and you're zooming in and out, it is using overviews. If you're zoomed out really far, the picture that you're seeing is small, right? And if you zoom in ever further, the picture gets bigger. And for that visualization to occur, those are all what we call overviews. There's an image built for every single zoom level. Okay, and with tiles, it's similar. Only instead of a tile is breaking up a map into equally sized squares, essentially. And so oftentimes this tiling and these overviews are controlled by a tiling server, or maybe directly into from the software that you're running, like ArcGIS or something, has an internal thing that does that. With COGS, that information is baked directly into the file format itself. And so if the COG is sitting in cloud storage and I'm at my laptop in another country, I can just say, hey, I would like to get that COG, and it can stream it directly to me and take advantage of the tiles and the overviews. And so what we call it HTTP get range request. In other words, it's streaming. It's the same thing that we're doing when we're streaming a video online. It's the same idea. Okay, so that's the basic concept. That same concept can be applied to point clouds, can be applied to multi-dimensional arrays, and it can be applied to vector geospatial formats. Okay, so this is how are COGS different from an XYZ or a web mapping tile server? So perhaps you've seen these XYZ map, or a Slippy map, sometimes they're called, or a web mapping service or a web mapping tile service. How is that different than a COG? Okay, well, the mapping services are primarily used for visualization, So if you're on a Google map or any kind of online map, that's pretty much what you're looking at. That is being, so it's really just for visualization purposes in terms of zooming in and out and panning around. It's really good for making the display come up quickly as you're panning around the map. But you're not actually getting the data. You know, if you're in the Google Map API, I can't actually get that map data. I'm just looking at it. And so the difference is cogs are actually streaming you the actual full data. And so that's the big difference. So I have here in summary, cogs are designed for efficient access to high resolution raster data. Here's the data, but we're going to stream it to you bit by bit. And then the other, like the tile services and the web mapping services are really just about efficient map display online. So that's the main difference. Okay, we're going to change topics completely. So again, this is just kind of a survey. We're going to go from one technology to another, not get too deep. Also along the lines of data sharing when it comes to this cloud native model is I want to mention something called Spatial Temporal Asset Catalogs, or STAC is the acronym. And so what STAC is, it's all about sharing data. It is essentially metadata. Right? Let's say I have a bunch of drone imagery in cloud storage somewhere, and Carlos has got a bunch of imagery on a different server somewhere else. You know, the whole world has got servers with data on it. And Stack is about like, okay, how do we find each other? You know, how do we connect all these people that have geospatial data in random cloud storage around the world? So what Stack is it's a JSON-based metadata standard. And so JSON is just it's easy for a machine to read. It's easy for a human to read. It's just lines of text that describe something. And so in this case, we use JSON and GeoJSON to describe any kind of geospatial asset. So there is a lot of people you might have heard of who are adopting this, like Microsoft is using it, Planet Satellite Imagery Company is using it, NASA is using it. So it's kind of a standard that a lot of people in the geospatial world, a lot of them outside of academia, are starting to rally around. Like, hey, this is a standard way we can describe geospatial data. And it's also a standard API. And so if you're an organization that wants to make data available in a more fire hose fashion through an API, there's also a Stack standard for that. Okay, so if we all describe our data in cloud storage using Stack, here's my little graphic trying to explain the concept. Okay, so I've got geospatial data in the cloud somewhere. I describe it with the Stack protocol. Carlos does the same thing, and then someone else, you know, has geospatial data in the cloud. We're all indexing our data with this JSON-based Stack. How do we actually find each other? Well, you still have to have some kind of like centralized hub, you know, to make this work. And there currently are two basic hubs for that. One is the stackindex.org. Let me just open this real quick. This is a website where you can find every other Stack catalog that's in existence. Pretty cool. Okay, and then there's the Radiant Earth browser. Let's find something to click on here. Okay, so this is kind of what it is. The browser can read the JSON files and then render it into this kind of pleasing website. So let's not get too deep. We're going to do an entire session on Stack in March. But the idea with Stack catalogs is just a standardized way basically to write metadata. And so we can discover and share geospatial data in kind of a standardized way. All right, we're at 223. Let's talk about cloud computing now. So cloud computing is all about moving your geospatial analysis away from your local machine and basically outsource it to some remote machine. and we call that a cloud. That, I mean, you could call it HPC also. It's a little bit different than cloud, but it's kind of the same idea, is that somewhere else across the internet is a much bigger computer that can probably do your work a little easier. And here are some advantages. We already talked about this a little bit, but let's just reiterate. So with cloud computing, you can avoid a lot of upfront cost of owning and maintaining your own IT infrastructure. It allows individuals to scale up or scale down their processing needs. You know, if you only have to do one giant process once a year, you really need to buy super expensive hardware. Cloud computing allows users to access their data and their applications from anywhere on any device at any time. And so I walk around now with just my little laptop, and I don't have to worry about where is my data at and where's my good processing. It's just all on the internet. It makes it much simpler. But if you are in a world or in a place where internet connectivity is challenging, then this whole model that we're describing here kind of breaks down. The idea of cloud native is that the internet has bridged the gaps between everyone and everyone's computer into one network, and we can work seamlessly across it. And another advantage is that it empowers us to work directly on the same stuff together in the cloud. You know, and the best analogy of this is Google Docs, how you can both tap into a document that's, you know, on a server somewhere in the cloud and work on it, you know, simultaneously. When I first saw Google Docs, my head kind of exploded. I was like, okay, that's the future. So it's the same thing with geospatial. We can do some of this stuff more collaboratively than we could before. Okay, and when it comes to the most prominent examples of geospatial cloud computing, the ones that we have to mention, of course, are Google Earth Engine and Microsoft Planetary Computer. We're going to do a session on each of these technologies a little later on, so we'll just touch on it now. So Google Earth Engine, of course, provided by Google. You do it all online in your browser. The difficulty and the learning curve for a lot of people is it's not really a GUI button-based type of experience. You know, if you come from point and click GIS, like ArcGIS, this is not it. Google Earth Engine is more set up for programmatic execution. It's either a JavaScript code or there's a Python API to do it also. So you kind of have to be familiar with those languages to do it. But there is such a large user base using Earth Engine now that finding help and finding code examples is really not that hard. You can get started, you know, in a couple weeks. If you're coming from pure scratch to how do I use Earth Engine, there's tons of tutorials out there. There's just a lot of resources. Come find us, you know, reach out to me if you're looking to need a little bit of help on that. What else about Earth Engine? It has a really large data catalog. And so huge amount of geospatial data is just already there on the Google Cloud, and it can be just easily brought directly into your project. It has huge computing capabilities. You know, as an example, I put, I don't know, 500 gigabytes of drone imagery into Earth Engine, wrote some code to do a classification, like identify different cover types. And with the click of a button, it did the classification across all of my images in about 3 seconds. And had I done that just on my local computer with my local everything, it would have taken weeks probably, because I would have had to have done it image by image. But with this, you can just like combine all the images into one, and then all of a sudden you have access to this massive computing power. So Earth Engine is really worth checking out, especially if you're doing satellite remote sensing. The satellite imagery, chances are like already there. So you don't have to get them at all. They're already just sitting there waiting for you to analyze them. So that is Earth Engine. Microsoft Planetary Computer is kind of Microsoft's answer to Earth Engine in a bit. I don't know, it's a little different though. Planetary Computer does have a very large data catalog also, but you interact with it basically through a Jupyter notebook. And you use existing tools. You use pretty much existing Python tools to do analysis. Whereas in Earth Engine, they have all these purposely built and specified, like they have tools that have been built specifically for Earth Engine. So you have to learn those tools. With Planetary Computer, it's, hey, we'll give you a huge, computer. We'll give you all kinds of data, but you bring your own tools to the party. But they're both quite interesting, and we'll go into pretty deep detail into both of them on different sessions. Okay, let's continue on the cloud computing topic here. So yeah, the two most prominent are Earth Engine and Planetary Computer. And then we just get into just, computing in general. This is not geospatial specific, but there's just a lot of access nowadays to different computing platforms. We've used Google Colab already in this session, or not this session, but this workshop. And so you can get direct compute, using Jupyter Notebook and Google Colab. GitHub Code Spaces it allows you to launch an instance of VS Code directly from a GitHub repository. So it does require a subscription. I don't think education gets it free, but it's another option out there. Let's see, Posit Workbench. That's a cloud version. It's mostly well known for RStudio. So you can do your RStudio stuff on the cloud and Posit. I think they also do Jupyter and VS Code in that. And then there's MyBinder, which I think is the same idea. I've never used Binder before, but I think it's pretty much the same thing as Colab. It's just you are across the internet, you are tapping into a larger computer and given space and compute to do whatever analysis you want. So yeah, I call those cloud-based integrated development environments.
What does VS Code mean?
VS Code is just a piece of software, Visual Studio Code. It's a product from Microsoft, and it's probably the most used IDE or integrated development environment out there right now. It's just a hub. If you're a developer, it's a hub for organizing all your files. So you can look at your entire file directory tree. You can access remote computers. It just becomes kind of like your centralized workstation if you're developing in any kind of way. Yeah, it's a really nice program. So it is developed by Microsoft, and of course GitHub is owned by Microsoft. And so they've integrated the two quite nicely. Okay, so it's 2:30. Do we have any questions about the general landscape of cloud computing before I go directly into Cyverse? So we talked about why are we using the cloud? What is it? We want to go from like the download desktop model to the streaming cloud model. We talked about storage, store your data in object cloud storage. We talked about sharing your data with cloud native formats. What is cloud native? What is data streaming? Then we talked about stat catalogs, which is metadata for finding data online. And then we talked about a little bit about cloud computing, talked about Earth Engine and Planetary. So yeah, if there's any questions in the chat, Carlos. Let's see. Nope. Okay. Oh, sure.
So between these things like geotypes, like the data types of the geotype versus Google Earth Engine, how are those similar, different, and why might you use one over the other?
Okay, the question was about differences between, you're talking about file formats, like what's the difference between a geotiff and the formats that are in Earth Engine? Okay. A geotiff has been around for a long time, and it's been very common in the traditional model of computing, and it's been very common for raster or raster data, array data. The first satellite data I ever looked at in 2006 or 7 was a geotiff. It's just a super common format. When I produce all of my imagery products for my drone, it's usually a geotiff. So often when I collect the data, it's a JPEG. So a geotiff is often a lossless way to store data in a raster or like an array format. And it usually is way heavier and requires more storage than a JPEG. But a JPEG often has some loss to it. Carlos, did you have some thoughts on that?
Yeah, the TIFF format is an image format.
Image, yeah.
GeoTIFF is just an image format georeferenced. So
Yep.
every image has a location
Yeah,
added to it.
and I guess more so, like, not specifically geotiff, but all of these data sharing file types versus what you've got on Google image. Is there like more difference in one?
Well, yeah, Earth Engine is kind of its own, wants to be kind of its own world. When you put your data into Earth Engine, I don't know what it's using. It's using some kind of cloud format, but I don't exactly know. What they're doing is proprietary, and I'm sure I could dig and find out exactly, but Earth Engine, you use it if you want to use this big computing platform for whatever reason. The other formats are something you'd use not in Earth Engine. If you're just making your own products or trying to share with other people or get data from someone else that's sharing. So that's outside of Earth Engine.
There's a question in the chat.
Question in the chat. Okay, I see it. Can cloud formats work with desktop formats? Can you overlay clip one format with another? With one format with another? Yeah, I don't think there's any problem with that. So let's say you're in ArcGIS or QGIS. You can stream a cog directly into that graphical user interface. And I'm pretty sure you could probably take just a shape file or some vector and clip it. So yeah, that's the idea with this cloud native, is that you stream it into your application. You don't download the whole thing. And so you're working with it in memory. And if you want to actually save it, you can save it to your local disk if you want. So yeah, I think that works, Elizabeth. You're welcome. Okay. Well, let's talk about Cyverse. So Cyverse was a mystery to me for a long time. I'd heard the word and I was like, what does that mean? So I work on the Cyverse project. What is Cyverse? I would just say it's cloud computing. It's a big computer in the sky. Actually, it's here at UITS. It's here on U of A's campus. It's a bunch of computers, and students, staff, faculty, or anyone can tap into it to use its large storage and computing resources. So I love the floating person logo here. Cyverse is all about, it's about trying to drive open science. It's an open science workspace for collaborative, data-driven discovery. So Cyverse, think of it as a big computer, is housed at the University of Arizona, and it's definitely a one-of-a-kind computing system for the academic and research community. So it started in 2008, I believe, is when the original funding started. And so it's been in existence for 16 years. It's spent $120 million in research funds. We have 135,000 registered users, and it has been a part of 1,700 or so peer-reviewed publications in several different scientific fields. It really started out specifically for plant science and plant genetics. It was originally called iPlant Collaborative. And then a few years later, they're like, why are we limiting ourselves to plants? And so it's, genomics has moved in, astronomy, geosciences, health, agriculture. almost every academic field or research field uses data. And so it seems like a lot of people would get utility from it. And so an important thing for anyone listening is that Cyverse is completely free for anyone affiliated with U of A. For students, staff, faculty, you can get in there and get yourself a really large storage allocation and have access to large CPU and some GPU computing resources. It's just all there for you. Yep.
If you have a project on Cyverse and then you leave U of
Uh-huh.
A, what happens then? Access to it, like if you were to like decide your
No.
No,
No, we're certainly not gonna like, oh, that person's not at U of A anymore. No. Once you've gotten access, you'll be grandfathered in forever, as long as we continue, as long as the project continues.
And the username is the email from the U.
Yeah, so your username would be your email. And you can just talk to one of us there. It's like it's not a problem. Okay, so we're not going to do a demo today. We don't really have enough time, but let me just take you through some highlights of why it might be of interest to you. To find out more, of course, go to the Cyverse homepage, which is cyverse.org. And then this link here is the a self-guided kind of tour. If you're trying to figure out more of the ins and outs, you can do that. But let me give you more of the highlights. Here's kind of a cool graphic. So there is Cyverse Public, which is just like regular Cyverse. It's a Cyverse I use. None of my data is sensitive. I'm like share, open, everything, open and free. But there are other fields that are not exactly like that. And so there is a Cyverse for other sectors like Cyverse Professional. There's Cyverse Health and Cyverse Defense. And those have different levels of kind of privacy and security and encryption around the data and you're computing inside the system. So if you're interested in using Cyverse, but you feel like it has HIPAA requirements, then you can still use Cyverse, but please talk to us and we can help you find the correct version. Okay, so why would you use Cyverse? My first pitch is data storage. So we talked about the utility or the benefit of cloud storage, and Cyverse is just a great example of it. And for U of A people, it's free. And if you want a terabyte of data storage, great, just ask me and you'll get it. So it's similar to the commercial cloud providers, costs a lot less. It has several different ways to do input and output. You can access things through a web page, or you can do it programmatically through the command line or through Python. So there's a lot of different ways to get data in and out. It makes all your data shareable through a single URL. So it's great for this cloud native data that we want to stream. It can be made, all your data can be made public or private. You can share it with anyone and you can set any permission levels that you want. If you do a project and you want that data to be permanently stored, like as a data repository, we can do that too. And so we have something called the data commons, where you can put your data, you can get a digital object identifier. Let's say you publish a paper and you have a data set that goes with it. You could put it in Cyverse, in perpetuity, basically, and get a DOI. So that's the number one pitch why you should use Cyverse, is just big data storage. Storage is an expensive commodity nowadays. All U of A people used to have unlimited storage in Google Drive. Guess what? That changed a couple of years ago. So now I have a total of 15 gigabytes in Google Drive, it works for documents, but for the data that I work with, I can't put drone imagery in Google Drive. And so the Cyverse data store is a great place for that. Okay, so that's reason number one, data store. Reason number two is the discovery environment. So the discovery environment is where we can actually do computing, cloud computing. And I guess what I would compare it to is like Google Colab in a way, or Posit Workbench. It kind of has that same kind of feel to it. So within the discovery environment, you can launch an instance of a Jupyter Notebook or QGIS or RStudio or VS Code or hundreds of other apps that people have made. And so the apps can be like just an executable app, like just a script, or it can be an interactive app like a Jupyter Notebook. And so you can launch those and do your science in a notebook. And it can be connected directly to the data store. You could have your terabyte of data right next to your compute, right next to each other. And so, yeah, you can do similar things on like Google Colab, but those commercial providers give you a free tier and it's usually small. If you want something bigger, it'll cost. With Cyverse, it is still free if you're a U of A affiliated person. So yeah, it gives you access to large CPU, some GPU, and memory resources. You happen to have big analysis you want to do, or small. It doesn't always have to be big. And then you have the ability to run your own containerized software applications, and that's a bit more advanced. So you can take any kind of piece of code or software, put it inside a container, which then allows it to be, it makes it portable and modular. And so you then can run it on any computer in the world, and you can run it on Cyverse if you like. But that is a bit more advanced. So that's reason number 2. There's a lot of computing resources. Okay, let's keep going. So Cyverse is a partner with Jetstream 2. So Jetstream 2 is it's national cyber infrastructure. So it's funded primarily by the National Science Foundation. And Jetstream 2 is just a really large cloud computing system. It's much bigger than Cyverse. So it's like our big brother in the sky or something. It's a very large cloud computing, and it's housed primarily at the University of Indiana. And you can look at this cool graphic, Internet 2. They've connected a bunch of these universities with faster internet connections. And that's how you access Jetstream 2, which is at University of Indiana. Anyway, if you are a funded researcher, if you've got funding from NSF or USDA or NIH or whatnot, you could probably get yourself a free computing allocation on Jetstream 2. For just the normal single researcher, this is probably not necessary. This is like, are you doing something bigger? You're processing lots of data. Do you have like a big kind of data operation? Jetstream is there and essentially free. Okay, another thing to mention is, well, I think that might be the last thing I mentioned, is cacao. So cacao is chocolate. It also stands for Cloud Automation and Continuous Analysis Orchestration. I haven't quite figured out what that means yet, but what cacao is, it is an interface for building virtual computing systems. Okay, so let's say you're on cloud infrastructure and you need to build 5 virtual machines that have 6 different kinds of software with this specific code and this specific resources. And so with Cacao, you can write a template, something called a Terraform template, and also use something called Ansible to basically build this template where a person can come in and go click one button, and then they can build this whole virtual cyber infrastructure to do your analysis, and then you can just tear it back down. So they call it infrastructure as code. And so it's a really fancy way to just build all this virtual infrastructure in terms of compute, storage, software pipelines. This is more advanced stuff. But again, if you're in the business of large computing, infrastructure as code and Cacao is a pretty cool thing. It is cloud agnostic, meaning you can run it in Jetstream 2. That's what it was designed to run in, Jetstream 2. But it could also work in commercial cloud like AWS, Azure, and Google Cloud. So Cacao is a product that was made in-house at Cyverse. And it's kind of one of our most interesting kind of developments, I think, the last couple of years. And so that's, I guess, the final reason. If you are at a super high cyber infrastructure level and you want to build giant, virtual computing worlds, you can. Most of us probably will not be going down the cacao route, but good to know that infinite compute is available at your fingertips if you need it or want it. Okay, it is 2:48, and that's pretty much all I had to say. So when it comes to Cyverse, these links will get you there. You can get yourself a login, and we can help you get an account. And the most simplest thing that you want to use it for is data storage, somewhere to put data. So I will stop here and answer any questions, either in the chat or verbally. So
I've got a brief question. When we go to make an account, it says the portal is undergoing maintenance. Just try again later.
yeah, today is a special day.
Oh, yeah, look at that. Maintenance is today. How about that? I
Yeah,
should have just read the pop-up.
yeah, the first Tuesday of every month, they basically, for several hours, they have to go in and do maintenance. And that's what's happening today. You can't imagine
Okay.
how many times that's like messed me up, where I'm like, okay, now everyone, we're all going to use it together. Oh no, it's maintenance day. So yeah, that's the
Well,
reason.
thanks for that.
Try tomorrow.
Okay.
Okay, any other questions? Let's see here. Yep, user portal is currently undergoing maintenance. Yep. Okay, well, thank you all. I'm gonna hang out here, are there any other questions?